Magnet, a material that generates a force field known as a magnetic field around itself. This field allows magnets to attract or repel other magnetic materials without any contact with them. A magnetic force is thus a type of non-contact force, just like the electrostatic force or gravity. A magnetic field can be visualized as invisible lines of force in a region of space around a magnet. These can be visualized by tracing them out using iron filings sprinkled on a sheet of paper that is placed over the magnet. These lines of force have arrowheads on them, representing the direction of the field, and they never cross each other. Any magnetic material, regardless of its shape, has two poles, a north pole and a south pole. These poles constitute what is known as a magnetic dipole. The term dipole refers to two opposite magnetic poles separated by some distance. For simplicity, I shall be using a bar magnet to represent magnets for the rest of this video, but in reality, they can be made in all shapes and sizes. The magnetic field around a bar magnet runs from the North Pole to the South Pole, outside the magnet. The direction of the field at any point tells you the direction that the North Pole of a tiny magnet placed at that point would experience. The force on the South Pole at that same point would be in the opposite direction. The strength of the magnetic field at any point is represented by the density of field lines at that point. The denser the lines, the stronger the field, meaning a greater force is exerted on other magnets at that point. We will discuss more on magnetic field strength in a later video. Magnets always exist as dipoles, meaning that even if you cut a magnet in two, each piece forms its own north and south poles. In theory, magnetic monopoles could exist, but none have ever been discovered. So, how do permanent magnets work? The answer lies within electrons inside the atoms of a material. All electrons have a fundamental quantum mechanical property known as spin. It can be thought of as the electron's intrinsic form of angular momentum, much like a tiny top spinning on its axis. However, it's important to note that electron spin is a purely quantum phenomenon and doesn't have a direct classical analog. Spin is a fundamental property of all electrons, just like charge and mass. Spin and charge produce an intrinsic magnetic dipole moment in each electron, whether it is bound inside an atom or not. Simply put, each electron behaves like a tiny bar magnet. Electrons bound to atoms also have another magnetic dipole moment. From classical electrodynamics, it has been established that a moving charge creates a magnetic field. Thus, as electrons zoom around the nucleus, their orbital angular momenta give them another magnetic dipole moment. Adding up these two dipoles yields a resultant dipole for each electron, and adding up these resultants for all electrons within any particular atom yields a net magnetic dipole for the entire atom. So each atom can be viewed as a tiny bar magnet as well. When these atoms come together to form crystals, doing so in such a way that their magnetic dipoles align. The dipoles add up vectorially to produce a net magnetic field around the entire object. What makes some materials magnetic while others are not? Well, electrons within atoms occupy discrete energy levels known as atomic shells. These are regions of space around the nucleus where electrons spend most of their time. Each shell can contain a maximum of 2 electrons, dubbed an electron pair. According to Wolfgang Pauli, any 2 electrons that occupy the same orbital possess opposite electron spin. This means that the magnetic dipole moments of the 2 electrons are in opposite directions, thus will produce no net magnetic field. On the other hand, an unpaired electron in an atomic shell produces a net magnetic dipole moment on the atom. So, substances with atoms that have unpaired electrons in their shells will produce a net magnetic field, while those without unpaired electrons produce no net magnetic field. Also, because electrons are evenly distributed around atoms, this means they are moving evenly in all directions around the nucleus, and thus no net orbital magnetic moment is produced in any direction. This explains why some substances are magnetic while others are not. When magnetic substances form crystals, they form regions where atomic magnetic dipoles align in the same direction. These regions are known as magnetic domains. When magnetic domains are pointing in different directions, their fields may cancel out, resulting in no net magnetic field, causing a magnetic substance to seem non-magnetic. When exposed to an external magnetic field, such as that of a solenoid, these domains are forced to align with the external field, like how a compass aligns with the Earth's magnetic field, thus causing the substance to become magnetic. To demagnetize a substance, you need to disarrange the domains by subjecting the metal to sufficient heat, mechanical vibrations, or a rapidly changing magnetic field produced by AC. There are three types of magnetism, namely ferromagnetism, paramagnetism, and diamagnetism. Ferromagnetism is the strongest form of magnetism and is responsible for the magnetic properties of materials like iron, cobalt, and nickel. In ferromagnetic materials, the magnetic moments of atoms spontaneously align in the same direction, even in the absence of an external magnetic field. Paramagnetism is a weaker form of magnetism, found in materials with unpaired electrons. Materials with this form of magnetism are weakly attracted to external magnetic fields. These materials have unpaired electrons, which means their atomic magnetic moments do not completely cancel out. At higher temperatures, the thermal agitation can disrupt the alignment of magnetic moments, reducing the material's magnetism. Diamagnetism is the property of materials that causes them to be repelled by a magnetic field. When an external magnetic field is applied, it induces a magnetic field in the opposite direction within the material, resulting in a repulsive force. Diamagnetic materials have no unpaired electrons, leading to a net magnetic moment of 0. If you enjoyed the video, please leave a comment, like, and subscribe for more content. That's it for how permanent magnets work. Thank you for watching.